Chance-Constrained Rapidly Exploring Random Trees, or CCRT STAR. My name is Paul Lathrop, and I'm a PhD student in aerospace engineering at the University of California, San Diego. My mentor at Los Alamos was Beth Boardman, and we are in the E3 group. I will be discussing implementation of the Chance-Constrained Rapidly Exploring Random Tree STAR algorithm. First, I will discuss RRT and RRT STAR, of which CCRT STAR is an extension. Next, I will present the CCRT STAR algorithm, then go into detail on several parts of the algorithm. I will then present some results and future work opportunities. CCRT STAR is an extension of RRT STAR, which itself is an extension of RRT. RRT is a random sampling-based path planner that chooses random points, connects the random point to the nearest existing point, and continues until the goal region is reached without running through obstacles. RRT STAR extends this algorithm by allowing rewiring of the created tree to reduce the cost to each node. RRT STAR converges to the optimal path as the number of samples goes to infinity. The rewiring function takes a non-optimal tree and tries to shorten the path length to each node. This is accomplished by examining every single node in the tree. For node I, the list is reordered from closest to I to furthest from I. A range of nodes in close proximity to I are then checked. The jth node in this list is assigned as the hypothetical parent of I. The distance to I is compared before and after the reassignment, and the shorter path is kept. Once each node j within the range is checked as a parent for I, the next node I is scrutinized in the same way. Increasing the range to check increases the optimality of paths, but comes at a cost of increased computation time. As you can see in this pair of figures, each node in the rewired tree on the bottom takes a more direct path to the start. CCRT STAR is similar to RRT STAR in that it is a random sampling-based algorithm that has rewiring for path optimality. However, instead of simply connecting points to one another with straight lines like RRT, a dynamic model and controller are taken into account. The dynamics model uncertainty in the state and uncertainty in measurements through tracking the state mean and covariance under a Gaussian distribution assumption. Once a random point is chosen, the dynamics and controller simulate the state from the parent point to the random point, and the resulting nonlinear path is checked for probabilistic feasibility against known obstacles. The furthest probabilistically feasible point is then added to the tree. Random points are drawn and simulated to until the goal region is reached. Then rewiring is done and the path is returned by tracing through the parents. A simple discrete time linear time invariant model is used to simulate the state. The state model matrices A and B are initially chosen as identity, but any model can be chosen. Control is inputted to the model with the U variable, and noise is introduced via the W variable. The covariance of the state evolves over time as a function of the previous covariance and the noise covariance model. The controller is chosen as a simple proportional feedback controller with gain K, and the controller magnitude is bounded from below to discourage asymptotic paths. Each obstacle is convex and represented as a conjunction of linear inequalities, where every inequality must be true to be considered inside of the obstacle. Conversely, to avoid an obstacle, at least one of the inequalities must be false, so obstacle avoidance is a disjunction of the converse of the obstacle definition. The objective is to reach the goal region with probability at least p safe. In other words, the collision probability at each time step must remain below delta, defined as 1 minus p safe. Since each obstacle is separate and being inside of an obstacle is a mutually exclusive event, it is sufficient to show at each time step that the collision probability for each of the B obstacles is less than delta over B. To add a node to the tree, the results of a simulation are analyzed. If every intermediate point is probabilistically feasible, represented by green dots in this figure, then the endpoint, or the randomly drawn point, is added to the tree. If the path becomes probabilistically infeasible, red points, the last feasible point is added to the tree, so the simulation is not thrown out entirely. If the first intermediate point is infeasible, the simulation is discarded and a new random point is drawn. To show that a given point or state does not have at least delta over b chance of being within an obstacle, the Gaussian curve is evaluated with respect to obstacle bounds. To do this, the Gaussian standard error function ERF is used to evaluate exactly how much of the curve is within the obstacle. It can be shown that the probabilistic constraint is equivalent to a deterministic constraint via the Gaussian standard error function. The probability that a random variable v is less than 0, for that probability to be less than some value delta over b, is equivalent to the deterministic constraint involving the mean of v, the covariance matrix of v, the function ERF, and the value delta over b. Therefore, this deterministic constraint needs to be evaluated for each obstacle for each intermediate point on the simulation path every time a random point is drawn. Even once a goal region is reached, more random points can be drawn in order to lower the path length to the goal region. In this way, CCRT star can be guaranteed to converge to the probabilistically feasible optimal path in the same way as RRT star does, as long as enough nodes are checked during the rewiring process. As is evident in the graph on the bottom, drawing more nodes in the tree lowers the path length to the goal region. Future work will include incorporating more complicated dynamics and controllers and building a cost function to include covariance information as well as path length in the calculation. Additionally, future work includes using CCRT star to output paths and training a deep recurring neural network on the paths and p-safe values. The neural network will path plan in the obstacle environment with no explicit knowledge of obstacles, dynamics, controls, or Gaussian assumptions. Additionally, a neural network can evaluate paths in a fraction of the time that a random sampling algorithm can take. Thank you.